right. 5 minutes
Ready?
for Simon.
All right. This animation is called Minimum Viable Warfare. At the bottom we have a base. It can fire a single shot in its defense. Raining down from the sky are missiles. Their sole intent is to destroy the base. This is the foundation of some kind of game or simulation, but I've only got 5 minutes. So let's tweak the parameters. Here the sky can fire 2 missiles at a time to try and destroy the base. This swings the odds heavily in the sky's favour. It's going to win quickly every time. So let's tweak again. This is more like it. Here the bases can fire as many shots as they want to try and defend themselves from the missiles raining down from the sky. An impregnable defense until you run out of bullets. And then it's just a matter of time, but I have not got much time, so let's tweak again. Full blaze. Everybody can fire as many things as they want to try and defeat their enemy. It's amazing, it looks like fireworks, but the astute JavaScripter will observe. The browser is starting to jank. What's a jank? It's nearly 2016 and you should all know what a jank is by now. Janking is when we ask the browser to do too many things in too little time and everything gets a little bit shaky. So let's see some diagnostics. There are 2 things going on. We have an update phase and a paint phase. In the update phase, we do all the math required to work out where our things should be on the screen. In the paint phase, we draw them to the screen. To achieve smooth animation, we need to do this 60 times a second. This gives us a time budget of approximately 16 milliseconds to do all of our work. If we exceed this time budget, the diagnostics go red and the browser starts to jank. But not all hope is lost. We're getting nearly 2,000 things on the screen 60 times a second before the browser even starts to break a sweat. In more detail, this is what we're doing. Forever and ever, we go update paint. This is called the game loop. But do not do it like this, because you will burn out your CPU. So instead, we use window.request animation frame. Here, we ask the browser to call us when it's ready to draw a frame on the screen. We update, we paint, and the process repeats. In an ideal world, the browser will call us 60 times a second, and we will get smooth animation. We have a set of variables we use to represent the universe we have created. We update these variables according to some rules. We use the values of those variables to tell us where to draw stuff on the screen. We clear our painting surface, we draw stuff to it. Easy, job done. But real life is never easy. There's no guarantee the browser will call us 60 times a second. It has other things to do, and we are not that important. So we have to work out the time difference between now and the last time the browser called us, and use that to create a scaling factor for all of our physics. If we do this right, and not all the edge cases are covered here, we will get smooth animation. When it's time to draw, we use the HTML5 canvas. We have an HTML tag. We get a reference to that tag from the DOM. We get a drawing context from that reference. We call methods on that context to draw stuff in your canvas, in your browser, on your screen. But to truly understand HTML5 canvas, we must understand how a computer display works. Back when the first Star Wars movie came out, computer displays were made out of a glass tube. One end of that glass tube was large and rectangular. On the interior surface of that large rectangle was painted a coke and phosphor. At the rear end of the tube, there was an electron gun. It would fire a stream of electrons down the tube towards the phosphor-coated surface. When the electrons strike the phosphor, they will cause it to glow temporarily. Wrapped around the stream of electrons was a set of magnets. These magnets can cause the beam to be deflected to any location on the front of the glass tube. Now, if you have a region of memory and you sequentially read the values of the bits from that memory and use the values of those bits to modulate the electron beam on and off as you scan it across and down the front of the glass tube, you can cause a representation of the values held in those bits to be painted to the front of your screen. This is how a bitmap display works. We call this a raster-scan display, the foundation of all computer displays in use today. But there is another way to do it. Back in the dawn of computing history, computers are far less powerful. You would implement your display in hardware. You would send a list of drawing instructions to your display circuitry. These instructions would cause the electron beam to be deflected around to the front of the screen, much like you would draw lines on a piece of paper with a pencil. This technique is called vector display. Vector displays have one amazing property. Simply by multiplying the intensity of the magnets that deflect the beam as they scan it around the front of the glass tube, you can cause the image to be scaled up and down with incredible ease just by modifying the value of 1 or 2 bytes of memory. To do the same thing with a raster scan display requires a lot of complex math. You have to calculate the position of every pixel you want to draw on the screen. Tragically, the technique of vector display has been lost to the sands of time. But HTML5 Canvas gives us the best of both worlds. We can rotate and scale and translate our images with incredible ease, throw bitmaps around the screen with wild abandon. And if you look closely, you will see vestigial move to, line to commands that are the direct descendants of the original instructions used to deflect an electron beam around the front of a glass tube. Just how much wild abandon, I hear you ask? Here we try and draw as many shapes on the screen as we can. We fill up the screen with shapes 60 times a second before it is drawn. Each shape is translated and rotated. We're getting 2,700 shapes on the screen in 5.5 milliseconds. If you're trying to do 60 frame a second animation, you still have 10 milliseconds left every frame to do all of your math. And JavaScript can do a lot of math in 10 milliseconds. Thank you. Woo!
with 5 seconds left. Brilliant.